Hello friends, in the last lecture we have discussed about maximum modulus principle. What maximum modulus says that if the function has a maximum modulus then it should be on the boundary, it should be not be inside, and if its maximum value lies inside the boundary then that function should be constant. That function should be constant. Okay, that we have seen for maximum modulus principle. Now we will go for minimum modulus principle. Now we will go for minimum modulus principle. Okay, that we will see for the minimum modulus principle. What says this minimum modulus principle? If f is non-constant analytic function, we are saying non-constant. F is non-constant analytic function in a bounded domain D and it is non-zero on D. Non-constant, non-zero. Then fz cannot attain in minimum in D. If any function is non-constant and non-zero, then its modulus is not minimum inside D. Is not minimum inside D. Minimum may be on the boundary of D, but not inside D. That we are finding. That we are saying. This is the minimum modulus theorem. This is the minimum modulus theorem. Suppose that f is analytic in domain D and it is non-zero in D. Then 1 by fz is analytic throughout D because f0 is non-zero. F is analytic, which is non-zero. 1 by fz is also analytic throughout D. Also 1 upon fz is bounded in D. Bounded in D. So by maximum modulus theorem, non-constant analytic function and it is bounded. Non-constant analytic and bounded, as f is non-constant analytic bounded, so 1 by f is also analytic non-constant and bounded in D. Okay, so 1 by fz is also bounded in D, and so if 1 by fz is bounded and analytic function in D, therefore by maximum modulus theorem, mod of maximum modulus of this function attains its maximum at some point on the boundary of D. On the boundary of D. So as maximum of modulus of 1 by fz attains at the boundary of D, that means minimum of this mod fz must attains on the boundary of D. That is, mod fz cannot attain its minimum in D. It should be attains in. So therefore, mod fz attains its minimum at some point on the boundary of D. That means mod fz cannot attain its minimum inside D. It should be in the on the boundary of D. The minimum modulus theorem says that if f is analytic in a domain D and non-zero and a is any point inside D such that mod of fz greater than or equal to mod of a, okay, at that point is point of minima, then your function should be constant. Then our function should be constant. Otherwise it cannot happen. Otherwise it cannot happen. So if your modulus is maximum inside, then it should be constant. If your minimum also inside, then it should be constant. So whether maximum value of modulus or minimum value of modulus, you are saying it is on the boundary there. It is saying on the boundary. For example, suppose that f is analytic function in a neighborhood of closed disk such that there exists m greater than 0 with mod fz greater than m for mod z equal to 1 and f of 0 equal to a plus ib with modulus of a plus ib less than m. Then show that f has a 0 in delta. F has a 0 in delta means what? F of z equal to 0 at some point z. At some point z in this delta. What is delta bar? It is a closure of that disk. So in a disk delta bar such that there exists m greater than 0 with mod f of z greater than m for mod z equal to 1 and f of 0 equal to a plus ib with mod a plus ib is less than m. So what which things we have? F is analytic function in the neighborhood of this disk, right? Such that there exists mod fz greater than m for mod z equal to 1 and f of 0 equal to a plus ib with mod a plus ib is bounded by this f. Then we have to prove that f has a 0 in that disk. F has a zero in disk, inside disk now. If possible, suppose F has no zero in delta. Then by assumption, 1 by F is non-zero analytic function in the neighborhood of delta bar. As F bar is non-zero, right? As F is non-zero in this delta, so 1 by F is also non-zero. As F is analytic, 1 by F is also analytic, and where F is non-zero, therefore. So it is non-vanishing analytic function in the neighborhood of delta bar, and therefore, if it is non-vanishing analytic function, it must attain maximum value on the boundary of delta. And what is the boundary of delta is mod z equal to 1. So the maximum theorem gives mod of 1 by fz is less than 1 by m, because mod of fz is greater than m. So mod of 1 by fz is less than m on mod z equal to 1. So capital M. So 1 by m will be the maximum modulus value of 1 by fz. In particular, 1 upon mod of a plus ib, if I took z equal to a plus ib, equal to 1 upon f of 0, 1 upon f of 0, because f of 0 equal to a plus ib we have given. Okay, f of 0 here, which is less than 1 upon m, which implies mod of a plus ib is greater than m. That is, m is less than mod of a plus ib, which is a contradiction, because we have given that m is greater than a plus ib. Why this obtained? Because we have considered f has no zero in this disk, and therefore f must have zero in this disk delta. F must have zero. Remark on above theorem means a non-constant analytic function in a domain cannot map an open set into point or an arc. If it is non-constant analytic function in a domain cannot map an open set into a point or an arc. Now we have one more corollary, that is maximum or minimum modulus theorem for harmonic function. Maximum or minimum modulus theorem for harmonic function. Suppose that u of xy is a real valued non-constant harmonic function on a bounded domain D. Then u of xy cannot attain its maximum or minimum value inside D. If u is a real valued non-constant harmonic function, then it cannot attain its maximum or minimum value inside D. If uxy attains maximum or minimum inside D, then u must be constant. Its meaning is like that also. That is, if there exists a point x0, y0 in D, such that u of x0, y0 is the maximum value or supremum value of u of xy for all z belongs to D, or u of x0, y0 is the infimum value of u of xy for all z belongs to D, then u of xy should be constant on D, should be constant. Then and then only it will happen. Should be constant on D. Suppose that D is simply connected. So we have taken u is a real valued constant harmonic function on a bounded domain D. So we will consider bounded domain as simply connected. Then there exists f analytic on this bounded domain with u is real part of f. With u is real part of f. And by applying maximum modulus theorem for g of z equal to e to the power f of z, because modulus of g of z is same as modulus of e to the power f of z, which is same as modulus of e to the power real part of f of z. So mod g of z equal to mod of e to the power f of z equal to mod of e to the power mod f of z, because e is constant there. That is e to the power real part of f, which is attains its maximum at some point on the boundary of D. That is u of xy attains its maximum on the boundary of D. Now assume that D is multiply connected domain. It will hold for simply connected domain. Now it will hold for multiply connected domain. That we have to. Cannot attain its maximum value inside D means what? It can have a maximum value on the boundary of or minimum value on the boundary of D. Now suppose D is multiply connected. In this case also, suppose on contrary uxy attains its maximum value at some point z0 in D. Since D is open, there exists a closed disk having center z0 less than delta in D. Then in this disk u of xy attains its local maximum at interior point x0 y0, which is contradiction again. Thus u of xy, because this is contradiction to that maximum modulus theorem, right? Thus u of xy cannot attain its maximum value in D. Applying the maximum case for minus u also, we obtain the result for minimum case. So if u is harmonic function, real valued function, non-constant function, which is bounded in domain D, then it has a maximum or minimum value only on the boundary of D, not inside the D, that is, or this set D. We have one result there. Consider u of xy is 2 times x square minus y square plus 3 for mod z less than or equal to 2. This we have taken D. Clearly u is harmonic on the disk, mod z less than or equal to 2. How we are saying it is harmonic? We know that when we say that it is harmonic, u is said to be harmonic if second times partial derivative of u with respect to x and second time partial derivative of u with respect to y equal to 0. Means Laplace, if Laplace equation is satisfied, then we say that the function is harmonic. So what about u here? Is it a real valued function? Yes, it is real valued function. It is harmonic. It is non-constant. Why harmonic? First derivative, we get 4x with respect to x. First derivative, second derivative with respect to x, we get 4. First derivative with respect to y, minus 4y. Second derivative with respect to y, minus 4. And their addition, 0. Now, to find maximum of u and minimum of u on mod z less than or equal to 2, it's sufficient to find these values on mod z equal to 2, because every harmonic non-constant function has its maximum or minimum on the boundary of that function, boundary of this disk. So only we have to check on the boundary of this mod z equal to 2. So for this, now we put mod z equal to 2 is what? It is a circle having center at origin radius 2. So let x equal to 2 cos theta, y equal to 2 sin theta. That is x plus iy, z equal to 2 cos theta plus 2i sin theta. So what is it? It is a 2 times cos theta plus I sin theta, e to the power 2i theta is. It is e to the power 2i theta. We can put having radius 2, isn't it? And center at origin, right? Or 2 times e to the power I theta also. Z equal to 2 times e to the power I theta. It is a circle having center origin and radius 2. Therefore, we have taken z equal to 2 e to the power I theta, that is x equal to 2 cos theta, y equal to 2 sin theta. We have u equal to 2 times 4 cos square theta, 2 times x square, 4 cos square theta minus 4 sin square theta plus 3. That is 8 cos 2 theta plus 3. For theta lies between 0 to 2 pi. When this, what about its maximum? When it will be maximum, this is, we know that less than or equal to 1. 8 plus 3 will be 11. So maximum value of u over mod z equal to 2 is maximum value of 8 cos 2 theta plus 3 for theta belongs to 0 to 2 pi, which is equal to 11, and it should be at theta equal to 0, because for theta equal to 0, this will be 1. 8 plus 3 is 11. In all other cases, it should be less than 1. So 8 plus less than 1 times plus 3 will be less than 11. And minimum value of u on this boundary mod z equal to 2 is 8 cos 2 theta plus 3, which is equal to minus 5. Because for this, if I consider minus 1, that is minus 8 plus 5, that is minus 5 at theta equal to pi by 2. And theta equal to 3 pi by 2. On these 2 points, this will be minus 5. If I take theta equal to pi by 2, what will happen? Cos pi is minus 1. That is minus 8 plus 3, which is minus 5. So minimum value of u also lies on the boundary of mod z equal to 2 at theta equal to pi by 2 or theta equal to 3 pi by 2, and maximum value of u lies on the boundary mod z equal to 2 at theta equal to 0 and theta equal to pi. Mod z equal to 2 means what? It is a circle having center origin and radius 2. So this is 2 comma 0. This is 0 comma 2. And your theta will be, so theta, where theta is 0, theta 0 is equal to 0 here. theta equal to pi. Pi means here, theta equal to pi, right, on the boundary. Theta equal to pi by 2, here, theta equal to pi by 2, on the boundary. Theta equal to 3 pi by 2, theta equal to 3 pi. Here, the point should be lies in here. Okay. So in all, it should be lies on the boundary. It should be lies on the boundary. Okay. Suppose that f and g are analytic on the closed unit disk mod z less than or equal to 1 such that mod of f of z less than or equal to m for all mod z less than or equal to 1. And 2, f of z equal to z raised to n g of z for all mod z less than or equal to 1 by 3 and for some n belongs to n. Find maximum value of modulus of f of z on mod z less than or equal to 3. This disk we have to find it. Okay, mod z less than or equal to 3. Now, suppose f and g are analytic on the closed unit disk mod z less than or equal to 1. Mod z less than or equal to 1. Right? Such that mod of f of z is less than or equal to m for all mod z less than or equal. Inside this z, mod f z is less than or equal to m. If fz is z raised to n times g of z for all mod z less than or equal to 1 by 3. Mod z less than or equal to 1 by 3 means this one, this disk we have taken. And for some n belongs to capital N, natural numbers. In this case, we have to obtain maximum of mod of f of z on this. In this disk, we have to obtain the maximum. We know the maximum on this disk is capital M. Now we have to obtain maximum of f inside the disk. Now on mod z equal to 1, we have mod of f of z less than or equal to m. That is m is greater than or equal to mod f of z, which is equal to z raised to n g of z, which is equal to mod gz, because mod z raised to n is again 1 on this mod z equal to 1. So mod gz less than or equal to also m for mod z less than or equal to 1. Now for mod z equal to 1 by 3, we have mod of f of z equal to mod z raised to n g of z, which is equal to mod z raised to n mod of gz, which is equal to, as mod z is 1 by 3, that is 3 to the power minus 1. So z to the power minus n equal to 3 to the power minus n mod of gz, which is less than or equal to m times 3 to the power n. So for all mod z less than or equal to m, even mod of gz is less than or equal to m. So if mod gz is less than or equal to m for all z in this disk, then mod gz also less than or equal to m in this disk also. That we have m upon 3 to the power. Thus mod of fz less than or equal to m upon 3 to the power n for all mod z less than or equal to 1 by 3. Therefore maximum of this mod of f of z for all mod z less than or equal to 1 by 3 is m upon 3 to the power n. It's m upon 3 to the power n. That we have obtained the maximum of mod of f of z. This is about minimum modulus principle. Okay. Once we obtain maximum modulus principle and then minimum modulus principle. Then we have one more important result which we call Morera's theorem. Before to see the statement of Morera's theorem, we'll see some introductory part. We know that if n belongs to natural number and modulus of a is greater than 1, then by Cauchy's theorem, I is integral over mod z equal to 1, dz upon z minus a to the power n is equal to 0. Is equal to 0. Because a lies outside this circle. That means 1 upon z minus a is always analytic in mod z equal to 1. And if your function 1 upon z minus a to the power n is analytic, we know that the Cauchy's theorem, if f of z is analytic, then integral over any curve C, f of z dz is always equal to 0. This result we know. If function is analytic on and inside C, then f of z, integral of f of z with respect to z on that curve C is always equal to 0. This is due to the fact that the integral I is analytic for all z in their delta, since mod a greater than 1. On the other hand, we know that integral over mod z minus a equal to r of 1 upon z minus a to the power n dz is 0 if n is included from 1 and it is 2 pi if n is equal to 1. That means what? Integral over mod z minus a equal to r of 1 upon z minus a. We have taken it is equal to 2 pi. We proved it is equal to 2 pi I. We know this. We prove it is 2 pi I. Now here your a is lies inside this circle, and in our case it was not, it was outside this circle. Here we have taken inside. If it is inside, we have two options. It is 0 for n greater than 1 and it is 2 pi for n equal to 1. This also we have already proved. Here the non-zero result arises because of the fact that integral j is not analytic in z equal to a, and this point lies inside the circle mod z minus a equal to r, which violates the condition of Cauchy's theorem. And for this we obtain your that Cauchy's formula here by using Cauchy's formula, isn't it? F n at a, F n at a is 1 upon 2 pi I n factorial upon 2 pi I integral over c 1 upon z minus a to the power n plus 1 d. Because by using this formula we will get this 0 here. Okay. Right. Now we will go for Morera's theorem, statement of Morera's theorem. Suppose that f is continuous in an open disk D with the property that integral over c f of z dz equal to 0 for each closed contour c in D, then f is analytic in D. If we see the statement of this Morera's theorem, then we can say that if we see the statement of this Morera's theorem, then we can say that this Morera's theorem is the converse of Cauchy's theorem. In Cauchy's theorem, we proved if f is analytic in domain D, which is continuous in an open set D, then integral over c f of z dz equal to 0. F of z dz equal to 0. And converse says that if function is continuous in an open set D, right? 1. So this is the converse of the Cauchy's theorem. It is the converse of the Cauchy's theorem. Means integral is 0, then f is analytic. Let a be an arbitrary fixed point in D. Since the integral is 0, holds for each contour c. So for any two contours c1 and c2 in D, which connect a with z1, we have. So we are connecting a to z1. We have 0 equal to integral over c f of z dz. But whole this c is nothing but integral over c1 minus c2. Why c1 minus c2? c1 in this direction and your c2 should be in this direction. Okay, c1 minus c2 f of z dz, which is equal to integral over c1 f of z dz minus integral over c2 f of z dz. This means that the value of, that means what? It is equal to 0 means what? Integral over c1 f of z dz is same as integral over c2 f of z dz. Integral over c1 f of z dz, which is a curve connecting point a to z1. And what about c2? c2 is the integral over second curve. Again that curve connects point a to z1. This means that the value of integral a to z1 f of z dz does not depend on the path which connects a to z1. Now define capital F of z is integral from a to z1 f of z dz for z belongs to D. Right? We will define a function capital F of z by using this integral from a to z1 f of z dz for z belongs to D. Since D is open, there exists an r greater than 0 such that a disk having center z, radius r is contained in D. Let mod h be sufficiently small so that z plus h belongs to the disk having center z and radius r. Z plus h we have taken here. Okay, this is z plus h and this we have taken z. It belongs to a circle having center z, radius r. Since integral from a to b f of z dz is independent of the path, we usually may write f of z plus h minus f of z equal to integral z to z plus h f of z d z. Independent of path means what? This is your means integral of this function at z plus h minus integral of same function of at z, which is these two, difference between these two. Therefore, f of z plus h minus f of z divided by h minus f of z equal to 1 by h integral from z to z plus h f of z minus f of z into dz. That this is just arrangement here. What about here? F of z plus h minus f of z upon h is nothing but 1 by h integral from z to z plus h f of z dz. 1 by h integral from z to z plus h f of z dz. Now minus f of small f of z means what? We have taken minus 1 by h integral from z to z plus h f of z dz. So if I take it, f of z is outside, and what is integral from z to z plus h of dz? It is z plus h minus z, that is h cancels with this. So this is just argument. Since f is continuous, it follows that mod of f of z plus h minus f of z divided by h minus f of z less than or equal to 1 upon mod h integral from z to z plus h mod of f of psi minus f of z into mod d psi. But what is integral over z to z plus h of mod d psi? It is the length of this curve. And what is the length of this curve? Which is mod h. So 1 by mod h and 1 by mod h, isn't it? Right? Here also it is mod h. So this is nothing but only f of psi minus f of z. As f is continuous, will tend to 0 as h approaches to 0. That is, f is differentiable with capital F dash z is equal to small f of z in this disk having center z radius r. Now since capital F is analytic in this disk, it follows from the Cauchy's integral formula for derivatives that f is analytic in this disk. Since z was arbitrary point of t, we conclude that f is analytic in D. Differentiable means what? Analytic. So if it is analytic at every point, differentiable at every point in the neighborhood of z also, then we say that it is analytic. So capital F is differentiable. Capital F is differentiable means what? Small f is also differentiable at z as well as in the neighbor of z. That means f is analytic in that domain. So this is called our Morera's theorem, which is the converse of Cauchy's theorem. Converse of Cauchy's theorem. Okay. And hence we have one more result, which is the corollary. We can call it as Riemann's removability theorem. Suppose that f is continuous on a domain D and analytic on a domain D which is apart from the point z0 for some z0 belongs to D, then f is also analytic on D. So what we have changes, suppose continuous on domain D and analytic on D except at z0, then f is analytic on D. It is enough to prove that result for the disk mod z minus z0 less than epsilon. By Cauchy's theorem for a disk, we have integral over c f of z dz equal to 0 for all closed contour c inside the disk mod z minus z0 less than epsilon. Apart from z equal to z0, since it is analytic everywhere, so its integral should be equal to 0. Hence f is analytic on mod z minus z0 less than epsilon by Morera's theorem also. And hence it is analytic there. Okay. So this is for Riemann's removability theorem. So we taken minimum modulus theorem and Riemann's removability theorem. So for this lecture, we will stop here. Remaining part we will see in next lecture.